So hello everyone, I'm Jared Turi, PhD student at Las Universidades under the supervision of Arthur Bitmono. And today I'm glad to present the work that has been accepted at IntEx this year about the guidance of a refinement-based acting engine with a hierarchical temporal plan. First, I will present what is a deliberative agent and how we intend to improve it. And second time, I will present IntEx, the system we have been developing, that is a refinement acting engine guided by planning, and I will finish with a short conclusion. The first, deliberative agent. I will start with a short definition of what is a robotic agent. We can define that as an entity capable of perceiving its environment, modifying its environment through the performance of actions, and deliberating, that is reasoning about its skills in order to fulfill goal. So what are the skills of an agent? A robotic agent is capable of elementary capabilities like move, grasp, look. And we can compose them as skills that are executable programs that we call operational models, like set the table. And all those skills will make the behavior of the robot. So to formalize that, we can formalize it in an acting domain where a tuple in a hierarchical fashion, where A is a set of all primitive tasks, so the elementary capabilities of the platform, T abstract tasks that are higher level of capabilities, like set the table, make the coffee, and MT is a set of methods where for each task, each abstract task are several methods to fulfill the high level goal of the abstract task. It's composed of preconditions and a body that is the execute table program that will be executed by the acting engine to fulfill the goal. So here is a short example here on the right, where you have a high level task that is open the door. You have two methods. Either you can push the door, or the second method, you can grab the handle and put it in function of the door. So to deliberate with such representation, we can use the refinement acting engine, that is a deliberation algorithms using hierarchical operational models. With such algorithm, an agent is able to perform multiple tasks in parallel and to do some automated deliberation. And here, in the present case, the refinement of tasks into methods. So we start with a high-level task with some parameters, and the refinement algorithm will map it to a method that is applicable in the current state with more parameters if necessary. There is some main algorithm, and here is a brief explanation of the main algorithm. So you receive, for example, a task TOW in the system. You add it to an agenda that is the collection of all ongoing tasks. You refine the task, which means you select an applicable method M for the task TOW. You progress M, and the progression is first to monitor the execution of M, or here you have an action. Then if you have a subtask, you refine again the subtask, and you monitor the execution of subtask. In case of failure, you resort to a retry algorithm that will call select again to get a new method that has not already been tried and progress the new method. And when all tasks and methods are successful, the high-level task is a success. The role of select is really important, as that's at this point that the system will select which method to fulfill a high-level goal. For example, here you have a bring a fork to the kitchen that will be defined in a method get and bring the fork to the kitchen with using the robot Ruby. So there is several techniques to select a method, the greedy one, that is the basic way of functioning, is to generate all applicable methods and to select an arbitrary one. But there is some problems, as it does not take into account long-term impacts of high-level choice and can lead the system to deadlocks. You can use also look-ahead techniques, that is the capacity to project the system from the current state to possible future states as planning. And that what we want to do is to use planning in the selection of methods. So that requires a planner and descriptive models of the agent skills. As we already have operational models of the agent, we need descriptive models that describe the set of states that may result from performing tasks. But there is some shortcomings with descriptive models in state of the art. They are made with limited dedicated languages as PDDL, HDDL, NML. And there is a shift in the presentation of operational model and descriptive model that makes the design harder. So what we want to do and what we propose in the paper is to extract descriptive model in the form of chronicles from operational model and to plan with a hierarchical temporal planner. To be able to extract descriptive models from operational model, it requires an acting language. So as it is an acting language, we need a kind of a general purpose language with an identified and simple semantics, so it's easier to analyze. So we choose to use a Lisp dialect, and it's invariant because it has few primitives, variables are immutable, it's purely functional, so it's pure, which makes the language really easy to analyze. To synthesize the proposition, the high-level proposition, we propose here refinement acting engine with a task refinement guided by planning. So the select algorithm can call the planner that will return a plan with the whole hierarchy refined and the selected method for the high-level task. And the second proposition is to extract from the acting domain the planning domain. So we only need to define an acting domain, both for acting and planning. So now I'm going to present OnPass, that is a neural implementation that can handle concurrency inside methods, and the refinement is guided by an HTM temporal planner. It uses a custom acting language to define acting domains, and here is an overview of the architecture. Here we have Ray that can that is linked to a platform. Here, for example, a robot can send commands, actions to the platform, and the platform will give back information about the action status and perception data. On the left, you have the monitor, that is the entry point, entry point of the system, where a human or program can send instantiated task to the system to be executed. So with this new rare implementation, we want to improve high-level choices by anticipating long-term impacts of high-level choices. So we want to improve select with a method selection based still on the applicability of methods, with an informed choice that accounts for long-term impacts, and taking also into account primitive task outcome thanks to a platform model. So from a simple selection method that just generate all applicable method and select an arbitrary one, we want to extend it with a select method that still generate all applicable method, but can also check in the plan which method was chosen by a planner. So the select method will first look if there is an already generated plan for the task. If there is not, it will call again the planner. And in any case, it will check in the plan what is the method that will be selected by the planner to refine the task. If there is a valid plan returned by the planner in the allocated time, we can use this method to refine the task. Otherwise, we resort to the set of applicable methods that has been generated and select an arbitrary one. So to use the planner as inputs, we need the state, the current state of the system, the task instance, the task we want to refine, and the planning domain. And as outputs, the planner will give back a hierarchical plan with all methods for every task refined and actions ordering, as this is a temporal planner. For that, we are using ARIUS. We have more detail in the paper. So the planning domain is made of abstract tasks and method, state function, and primitive task. And here is a little checkpoint in this presentation. For the moment, I presented the OnPass, the new implementation, and how we intend to extend the select methods in the refinement acting engine. And now I'm going to present the acting language from which we can extract chronicles and an example using plan. So as said before, we use an implementation of schemes that we call scheme OnPass, from which we can define an acting domain. First, we can define task with a label and type parameters, methods with label, type parameters, preconditions, and the body. And the body will be the part of the method that will be executed during the execution of methods. That's the executable part of the operational model. We also have state functions with label, type parameters, and result, and actions. There is also other facilities to define lambda, type, and constant in the execution environment. SunPass is also an acting language, and today I will present some acting primitives that interest us in the present matter, like exec task to execute and monitor a task. For example, if it's a primitive task, it will request to the platform the execution of a command. And if it's an abstract task, it will select a method and execute the operational model. We state that return the value of a state variable. So from this language, dedicated language to this new implementation, we want to come from an acting domain to a planning domain in the form of chronicle templates and state functions. To do that, there is a two-step transformation. First, we translate in a single static assignment form that is a lower level formalism, thanks to translation rules. All the rules are in the paper. And then from this formalism, we extract from the SSL form chronicles and post-process the chronicle thanks to extraction rules. Here is a simple example here. We have an expression that is the computation of the addition of X and Y variables. It results in this SSA form where each symbol is considered as a constant, and the application of the first constant to R2 and R3 is the result of the whole expression. As a result, we have a chronicle with a set of constraints where R2 is equal to X, R3 is equal to Y, and R is equal to R2 plus R3. So from that, here is an example of what we can do and how we can define a domain for a simple example. Here we have a gripper door problem where Ruby needs to place balls in different rooms that are connected through doors. There is 3 actions. The first one is to move. You can pick a ball and drop the ball. There is 4 state functions. The first one is to state the location of the robots, a location of balls, what gripper of Ruby carry, and how doors are connected. So the connected state function represents the topology of the problem. There is two tasks. The first one is pick and drop. That is the high-level task of the domain with only one method. First, Ruby move to the location of the ball, pick the ball, move to the targeted room, and drop the ball. And there is the second method that is a second task, sorry, move with two methods. Our first one that is no op if Ruby is already in the targeted room, and M recursive that will first move in a room and call again the high-level task to move. Here is an example of one method. It's not one of the method, but it's for the example, it has been simplified. So this method move to the location of the ball, check the good position of Ruby, and pick the ball. So in some paths, it would look like this. Here, this is part of the SSA form where each constant is translated. We have the restate here corresponding to this computation, which results in the following chronicle template. We also need a platform model for the system, and just for this example, we use a PDL fashion way to define primitive actions. We add as a primitive to represent effects, but it can only be used in the action model. So here we are the move operational model, where we have something looking like PDDL with parameters, preconditions, and effects, and the resulting chronicle. So we benchmarked on this domain on programs of different sizes, and we compared the refinement acting engine with three different selects. The first one is the greedy one, where you generate all applicable methods. The second one is using ARIAS. And the last one is optimal ARIAS, where the planner return an optimal plan. There is two metrics. The first one is the executed number of actions. And the second one is the total refinement time for at each step of the system. So we can see on both the plots that both ARIAS and ARIAS opt outperform the system in greedy mode. So we can state that it is really promising to use the planner because it does not increase the refinement time, and the number of actions performed is really lower. So now let's conclude on this work. On pass, so this the present system is an acting system with a new implementation of the refinement acting engine capable of using planning to guide refinement of tasks using a custom acting language from which we can extract descriptive models. Here is some perspectives. We want to have extraction rules for all primitives of the language. Compared with other techniques, notably other implementation of array like OPOM or run lazy refine ahead. It takes into account error handling from operational model into the chronicle encoding. We also want to test on more complex problems like a job shop simulation in array. And here I have a video. I don't know if you can see it. Maybe, oh, maybe I have to change what I
Yes, we can.
Oh, you can see it? Okay, all right. So here is the system working with in a job shop simulation where you have robots treating packages. And this is just working in a reactive way. So there is no intelligence in which packet and in which order. And we want to use planning in such a scenario. So thank you for your attention, and please feel free to ask any question. Thank you.
Thank you very much. Let's thank the speaker, and I invite anybody to ask questions. Okay, I have a question actually. So we saw ARIES and ARIES opt, but in the graphs that you showed, there seemed to be basically no difference, or in fact, in I think one of the graphs, there might be ARIES actually outperforming ARIES opt. Could you talk a little bit about what the differences between the two of them?
Well, the planner can just find a first plan that is a satisfying problem. Then there is the optimizing problem, where here we want to optimize the next plan. But in this problem, the planner was already finding the optimal plan, and it just needed a few more time, but it was really tiny to prove that the plan was optimal. That's why we have both graphs that are similar.
Okay. And again, any questions from the audience? Okay. If not, I have another question. So why did you choose the hierarchical planner? Because you decompose the domain into primitive actions. So couldn't you have done then the planning with a regular PDDL-like planner instead of a hierarchical one?
Well, we want to use a refinement acting engine. That's the first thing we want to do, where you have a hierarchical representation of operational model. So basically what we want to do is not to generate a plan, but to see in the skills, capabilities of the robot, which method is the best. And to do that, we generate a plan to verify that by choosing the high-level method, it will not lead the system into deadlocks. So the hierarchy is really interesting here.
Okay, thank you.